Hello everyone, welcome back to my YouTube channel. If this is your first time here, my name is Lizzie and I like making chemistry videos on things that are somewhat confusing, but I'm here to make them easier to understand and more accessible. This video will be a continuation of my last video on electrophilic addition of conjugated dienes, but I'll be going more in depth on the relationships between the stability of carbocations, alkenes, and how they result in the major or minor products under kinetic or thermodynamic control. And before I dive right into the video, I'm just going to say a couple things about me. I am an undergraduate student at Florida Atlantic University in Boca Raton, Florida. I'm currently getting my Bachelor's of Science in Biological Sciences. I am also in the honors program at FAU. I am a pre-medical student intending to take the MCAT in the next 5 to 7 months, hopefully. And I really like learning and teaching chemistry. To understand the major minor products under thermokinetic conditions, it's important to understand the stability and reactivity within carbocations or alkenes. Well, our carbocation stability depends on substitution. Tertiary carbocations are most stable, followed by secondary, primary, and then the methyl group. This happens because alkyl groups can donate electron density through hyperconjugation and inductive effects, which helps stabilize the positive charge. The keynote here is that the more stable a carbocation is, the less reactive it tends to be because it's already favorable in that substituted position. On the other hand, a primary carbocation is very unstable and therefore much more reactive since it strongly wants to stabilize itself by reacting. The same idea applies to alkenes on your bottom left corner. Alkenes are also stabilized by substitution, so a tetrasubstituted a double bond is more stable than a trisubstituted and disubstituted, and finally a monosubstituted alkene. On the energy diagram, where the y-axis is Gibbs free energy and the x-axis is the reaction progress, the kinetic product forms through a lower activation energy, so it's produced faster. In this case, the electrophile attaches to the most substituted carbocation, but the double bond left behind is less substituted and less stable. The thermodynamic product requires a higher activation energy, so it forms more slowly, but the result is a more substituted alkene at a lower Gibbs free energy, making it more stable overall. And to summarize the following relationships between carbocation and alkene stability with reactivity, the thermodynamic conditions is the most stable product produced, and it is the most substituted alkene. Major products are formed at higher temperatures between 25 to 40 degrees Celsius, and they usually result in the 1,4 addition. Not always the case. You're going to look at the more substituted alkene when viewing the major and minor products under thermodynamic conditions, and it has a slower reactivity. Okay, so in our first problem, we're going to do an acid-catalyzed addition of a conjugated diene, where the H2O over diluted H2SO4 is going to form that hydronium reactant, which is going to be attacked and deprotonated by one of the double bonds of this conjugated diene. So what you have here is that one of the double bonds of this diene is going to grab onto that hydrogen, and the sigma bond between the oxygen and hydrogen is going to break, pushing those electrons back onto oxygen, forming H2O. Now you can have it either way. You can have it that the hydrogen adds on the end, leaving that positive charge on a tri-substituted carbocation, or you can have it that the hydrogen attaches to the tri-substituted carbon, leaving it a primary carbocation. Now I'm going to strike this one out. I drew it in just for purposes to show you, but I will strike this one out because there is no resonance within the structure. If this double bond moved here, then this carbon will break the octet rule and it will not be able to move that double bond there. It just wouldn't work. There's no resonance there. So what you're left with is this carbocation. And now you can draw the resonance structure with this one. Now see, with this one, you can move the double bond over where the carbon is not breaking the octet rule, and that becomes a primary carbocation on the right-hand resonance structure. Now this is where the H2O will be attacked again, but this time not to deprotonate, but to form a bond between the oxygen and that carbon. And that's leaving it positively charged. And now a bisulfate ion is going to deprotonate one of the hydrogens, and the sigma bond breaks, shifting those electrons back onto oxygen, leaving you with this final product. And now if we do it for the other resonance structure, where it was a primary carbocation, once again, the water is attacked, specifically the oxygen is attacked, and a sigma bond will form between them, leaving that positively charged. And now another bisulfate ion is going to deprotonate one of those hydrogens. And like the other one, the sigma bond is going to break, pushing those hydrogens back onto oxygen. So what you're left is here is a 1,4 product, which is your thermal product. And here you have your 1,2 product, which is your kinetic. If you notice here in the thermal product, they added in the 1,4 addition, which we can conclude is the thermal control. However, we can also see that the double bond of the alkene is the most substituted. So here has 1 carbon, 2 carbon, 3 carbon, 4 carbon. Here it is tetrasubstituted, which means it is the most stable alkene. And what do we know is that the most stable alkene is going to be your thermal product. If you look on this one, this carbon is attached to 1, 2, 3. It is tri-substituted, and it is the most stable tertiary carbons are more stable than, we know secondary and primary. So this one is going to be your kinetic control or your kinetic product, because the hydroxy group is attaching to the most stable carbocation, but the alkene, if you look at the alkene, it is only primary substituted. So this is going to be a result of this reaction. Okay, so in this next problem, we're going to react 1,3-pentadiene with hydrochloric acid. One of the double bonds is going to attack and deprotonate that hydrogen, leaving you with 2 ways that we can put this hydrogen in. We can put it on this side, leaving a secondary carbocation there, or we can put that hydrogen on this side and leaving this one as a secondary carbocation. But like the other problem, there is no resonance here. This double bond cannot shift this way because that carbon is already attached to 4 different bonds. So there is no resonance in that structure there. Okay, so now we have our preferred resonance structure. Preferred carbocation. And now we're going to make that resonance structure. So let's say we move that double bond that way. This leaves it a positively charged primary carbocation. Cool. So these are your 2 resonance structures. Now we're going to do the same thing. This halide chlorine is going to be attacked by the positively charged carbon, forming this product. And we're going to do the same on this side. So how do we know it's a thermal or kinetic product? Well, you can look at the addition. So here, 1, 2, this way, 1, 2, 3, 4. This is going to be in the 1, 4 addition. And this is going to be in the 1, 2 addition. And noticing on this compound right here, it is not the most substituted alkene. It is only monosubstituted. On this carbon, or on this compound, I would say actually, this alkene is disubstituted. So it is going to be the most stable product in this reaction. And it is also going to be your thermal product. And you could also notice here that on this side in your kinetic product, your chloride is attaching to your most substituted carbocation, but it has the least substituted alkene. On this side, the chloride is attaching to the least substituted carbocation, but it has the most substituted alkene group. And that's how you know the difference between these two. Okay, in our last problem, we're going to react 4-methyl-2,4-hexadiene with HBr. And like in the other problems, there are 2 double bonds, so this can happen in 2 different ways. So if that double bond attacks that hydrogen, the hydrogen can attach here, leaving it a secondary carbocation right there, or the hydrogen can attach here, leaving it a secondary carbocation there. Like the other problems, there is no resonance with this one. You can't move the double bond this way. It just would not work. So we're striking that out. So we have formed the correct carbocation here, and we can make it resonance. All right, these are our 2 resonance structures. Now, what if we have attacked the other double bond? What if we did this? Well, let's analyze that as well. So if the hydrogen adds here, then you're leaving this with a tertiary carbocation. Or you could have had it that the hydrogen added here, leaving this secondary. But like the other ones, no resonance here. You can't shift this double bond this way because this carbon would break the octet rule. That would not work. So you're left with this carbocation. And now we can draw its resonance structure. If we move this double bond that way, now this leaves it as a secondary carbocation. And now you're dealing with 2 different types of carbocations and resonance structures. You have this one here, and you have the one that we did up top. So how do we differentiate which one will form our most stable products? Well, we can see the type of substitution on the carbocations. So in this structure here, you have a tertiary substituted carbocation. On this structure, you have a secondary. On this structure, you have a secondary. And on this structure, you also have a secondary. Since the one above has a ratio of 3:2, the bottom has it 2:2, you can pick out that this is probably going to be your most major product, or major products. So we can strike this one out, and we can deduce that this is going to allow us to give us our major product. So the positively charged carbon is going to attack that bromide. Leaving you with this as one product. And if the same happens on this one, it's leaving you with this product here. Now we can count how far away they each are. So you have 1, 2, 1, 2 addition, and here you have 1, 2, 3, 4. 1, 4 addition. Now let's look at the stability of the alkenes on each product. So the alkene on the right side is tri-substituted. The alkene on the left side is only di-substituted. And the most substituted alkene is likely or highly likely to be your thermal product. If you look on the left side, the bromide added to the most substituted carbocation, which would infer that this happened at a lower activation energy and most likely is your kinetic product. So with your kinetic product, your your electrophile is going to attach to your most substituted carbocation, leaving the alkene in that compound to be less substituted. But in your thermal product, in this case, bromide is going to attach to a less substituted carbocation, but have the most stable alkene. In this case, it had a tri-substituted alkene. And in this one, it had a secondary. So we can know that the left side is your kinetic product and your right side is your thermal product. And when choosing between which two groups of resonance structures to pick through to find your major product, always look at the stability of your carbocation. And usually it's going to be 3-2 or 3-1 over 2-2. What you want is your most substituted carbocations. That is going to give you your major products. And these are likely to be your minors. And that's this mechanism for this reaction.